Welcome to the webinar of Optimizing AHU with Delta Temperature Limiting. Dear attendees, a very warm welcome to our online event. Our topic for this webinar is Optimizing AHU with Delta Temperature Limiting. Today, we are happy to invite engineer Arul Hisham, principal and founder of AHU Consultants, to present us the topic, and he will also answer all your questions you may have. This is Andy Chan, Human Resource Manager of Asia Pacific, and I'll lead you through the webinar and moderate it. Questions can be placed all the time and will be anonymous. Type them in the question field. We'll answer them at the end of the presentation. In case the question field is not fully visible, you can fully open the text field by clicking on the question header arrow button. The display control panel can be expanded by using the orange button. You can keep the control panel maximized by deactivating the Auto Hide the Control Panel feature. You can find this option in the menu view. So that's it from my side so far. I'm now glad to hand over to engineer Arul for his presentation.
Testing. Thank you, Mr. Moderator, Andy Chan. Thank you, Bellimore, for inviting me to present in this webinar. I hope all the attendees are in good health and be protected from the COVID virus. A very good afternoon to all of you. Before we proceed further, the organizer has two polling questions for the audience. We would appreciate if you could answer the questions. You are given about 5 to 10 seconds each for each question. The question will be flashed on your screen. Now, the first question, which of these valves would you use for capacity control of a cooling coil? A, a three-way valve. B, a two-way valve. C, a two-way on-off valve. And D, all of the above. Now, the second question is, have you ever measured the chill water flow rate into your cooling coil during operation? It's either A, yes, or B, no. I hope you can answer the question. The Secretariat will flash the result of the poll on your next screen later. Okay, good. Thank you very much for your cooperation. This is the outline of my presentation today. With the current COVID-19 pandemic, it is more than ever that we need to control the air inside the building. Most people think air conditioner is mainly to cool the air. Actually, air conditioning needs to control not only the temperature and humidity, but also cleanliness, odor, and gaseous content of the air, or IAQ, indoor air quality. In this presentation, we will look at the reasons why we need to control the IAQ. In order to control the IAQ, we need to understand the behavior of the air. We will also look at the effect of temperature and humidity and how they factor in when equipments are selected. I will also share some case study on some survey on IAQ in buildings. Lastly, we will look at a case study also on an energy saving using the energy valve. Firstly, why do we need to control indoor air quality? Good indoor air quality is desired for a healthy indoor environment. We spend most of our time indoors. At least 1/3 of our time is spent in air-conditioned workplaces in Malaysia. The Malaysian Department of Occupational Safety and Health has issued a code of practice on indoor air quality back in 2010, which defines acceptable indoor environment parameters such as chemical contaminants, physical properties, biological agents, and radiation. In this code of practice, it is the onus is on the employers and the building owners to provide safe working places to occupants in air-conditioned building. Therefore, it is important that the air conditioning system is designed to meet all these requirements. In addition, the mechanism for identifying, assessing, and controlling indoor air pollution and occupational safety and health measures are also outlined in this code of practice. The parameters are spelled out in the following slide. These are the parameters. On the left are the physical parameters, the temperature, relative humidity, and air movement. And on the right are the list of chemical, biological, and ventilation performance indicator using the CO2 levels. There are also biological parameters on biological bacteria and fungal counts. Note that this code of practice is meant for officers, not for health or production facilities, as these facilities require more stringent requirements. Now, air conditioning system also plays an important role in disease prevention and treatment. The air conditioning can provide pressure control, dilution effect, clean air quality, proper humidity, flow pattern, organism viability treatment, temperature control, control of exposure time through air turnover rates. These are some guidelines that we use when designing air conditioning system for health facilities in Malaysia. Guidelines for design and construction of hospital and healthcare facilities, known as the FGI guidelines, from the Facility Guidelines Institute. ASHRAE Standard 170, ventilation for healthcare facilities. Guideline on conceptual design and engineering requirement for isolation room by the Ministry of Health, Malaysia. Guidelines on conceptual design and engineering requirement for central supply unit, also from the Ministry of Health Malaysia. Guidelines on mold control and remediation in healthcare facilities by the Engineering Services Division, Ministry of Health Malaysia, and also guideline on the prevention of mold growth in building by the Public Works Department, Malaysia. Notice that the last two guidelines make references to mold control in building. This is very important for high humidity countries like Malaysia. The COVID-19 pandemic has given buildings professionals bigger challenges. From these AHU guidelines on COVID, we know that COVID can still be viable on surfaces for 2 to 3 days, depending on the environmental conditions. The world has spent most of the research funding on finding a vaccine and effective drugs. Although these efforts are important, it must be accompanied by research on how to target and improve other non-drugs options that include the built environment such as ultraviolet irradiation, ventilation, and air conditioning circulation. For example, AHU recommended higher air change rate to reduce the possibility of infection. If the air change rate is 10 times per hour, it takes 41 minutes to remove airborne contaminants up to 99.9% efficiency. The higher the air change rate, the faster the removal of airborne contaminants. In March 2020, a group of researchers from China conducted a research on transmission of COVID through aerosol. They investigated the transmission of COVID virus in an air-conditioned restaurant and the effect of the ventilation and air movement inside the restaurant. They found out that the ventilation and airflow are very important to minimize the infection through the air conditioning system. What about air humidity in controlling transmission of pathogens? This graph shows the relationship between relative humidity and virus activation. There is a relationship that between temperature and there is a relationship between temperature and humidity in controlling virus. Say if the temperature is 20 degrees Celsius and 50% RH, there is a significant drop in virus inactivation compared to higher humidity levels. This study shows that at a relative humidity of 50%, less than 1% of the virus survive after 2 days. Now, let us learn the behavior of air. So we know that temperature, air distribution, ventilation, and humidity play important functions in controlling infections. Although temperature and air distribution is well understood, I found that the understanding and care about moisture and gases contaminants in building are still lacking. With the COVID pandemic, we need to put more effort on controlling the humidity more closely. Normally, as a designer, we only consider peak dry bulb as the design condition. However, if the building is operated in the tropics, where high humidity is common, peak dew point must be also considered. For example, in Kuala Lumpur or Singapore, there is more occurrence of high humidity than there is occurrence of peak dry bulb. From the psychrometric chart above, you can see that peak dew point condition occurs 10 times more hours per year when compared to peak dry bulb. At peak dry bulb condition, the moisture content of the air is 20.5 gram per kilogram of dry air. and at the dew point condition, usually 28 degrees C and 90% humidity, the moisture content of in the air is 21.5 gram per kilogram of dry air. So you can see that there is 5% more moisture in the air than that we need to dehumidify. When we compare these two conditions, the cooling coil requirement requires 26% more capacity for dehumidification. This actually will affect the overall cooling capacity by additional 6%. Another important concept that we need to understand is surface humidity. Material can absorb moisture directly from air when relative humidity is high on the surface. Condensation occurring on the surface usually leads to mold growth. When the surface RA stays above 80% for more than 30 days, mold growth is a risk, even without condensation or other wetting to start the growth cycle. Surface humidity is not the same as air humidity. Although the air is 55% relative humidity, which appears to be no problem, but the surface humidity is over 90%. At surface temperature of 19 degrees Celsius and the dew point of air is 18 degrees Celsius, they are too close that this will lead to condensation on the surface. Why do we need to deliver drier air? It is important that we deliver drier air just like we deliver cooler air when the space temperature set point. This drier air will absorb internal moisture, therefore resulting in proper humidity in the space. Well, you wouldn't want to wear a mask in your office, would you? I am sure you would not. Here are some examples of IAQ issues for my previous projects. Okay, this building is a 22-year-old public building. Our job was to audit the performance of the air handler as the owner was getting some complaints from the user. The building operates 24/7. In this project, we plotted space condition on ASHRAE thermal comfort chart, and we compare with the condition superimposed with the Malaysian standard 1525 in blue color and the client own requirement in the black lines. We found that only 5% of the space are within the client's requirement, 37% falls within the Malaysian standard, and 58% fall outside both the standards and the client requirement. In most of the conditions, they show high relative humidity, more than 65%. As you can see, the moisture content is higher than 0.012 kilogram per kilogram of dry air. These are the spaces, environmental condition inside that building at various locations. We measured the parameters over a period of 14 hours from morning to late night. As can be seen, although the space dry bulb temperature are within comfort limits, the RH varies between 50 to 88%. For example, at floor 3, the conditions are 25 degrees C and the RH is 88%, which is very high. Okay, this is another example at another building, building number 2. Similar conditions. At the third floor, the humidity is as high as 82%. Most of the spaces' humidities are more than 70%, especially at night. Here are some of the photos during our site survey. You can see that there are some mold growing on the diffuser because of condensation. We found out that this is very prevalent in this building. We also found fungal growth on the air conditioning duct inside the AHU room and also on walls. This happened when the wall is between air conditioned and non-air conditioned building and air conditioned area. Now, another job that we did was at a hospital. In this particular case, we found fungal growth on the ceiling. And this hospital is quite recently built. Yeah, it's not an old hospital. It's about 2 to 3 years old. Photo on the left shows a bad installation of duct connection to the diffuser. This is because there was insufficient turning radius for the flexible duct. Therefore, the duct lies on the ceiling and the air diffusion is not uniform coming out from the diffuser, resulting in colder temperature on the ceiling surface, on one side of the ceiling surface. And as you can see, the surface temperature is 16.5 degrees Celsius. Also at this hospital, you can see that condensation had occurred on the ceiling tiles inside the ceiling space, which resulted in fungal growth. Now, let us look at the interaction between equipment for temperature and humidity control. How do we control our cooling coil? This is a typical piping connection at a cooling coil. We install a balancing valve to ensure that the coil gets the correct flow and not overflowed, and a pressure independent modulating valve to control the amount of chill water going into the coil. Normally, there is no flow measuring device to actually measure the flow, as the flow meter is quite expensive. So how do we know how much flow is actually going into the coil at different cooling coil loading? We cannot do that, right? Many people think that by overflowing the coil will improve in capacity, but that is actually a myth. Okay, this is a typical cooling coil performance curve. Okay, cooling coil performance curve depends on various factors: chill water supply, flow rate across the coil, coil surface area, and etc. Assuming a coil is sized for 45 °F chill water supply temperature and 10 °F delta T, the coil output is 100% when it receives 100% of flow, which is at the design chill water supply temperature at point number 2. Yeah, the same coil can give 100%, 115% capacity if the chill water supply is lowered to 42 °F. See at point 1. However, if the chill water supply temperature rises to 48, its output will become 85% capacity, which is at point 3. Okay. Now, if the coil receives lower chill water supply temperature at 42 °F, the chill water required is only 70%. to give the same capacity at that point 4. Now, the coil characteristic is not linear. For example, at 20% flow, the coil capacity is 50%. Imagine if you oversize this coil and the actual load is lower than 50%. You may get the valve hunting as the flow is lower than 20% of the rated flow. These are the characteristic curve for a typical cooling coil. We are looking at, on the left is the capacity versus flow, and on the right is the differential pressure versus flow. When the cooling coil load is 70%, the required flow is 40%. At a flow of 40%, then the pressure differential acting across the control valve is 84%, with only 16% left in the system fittings. Okay, so the small change in cooling load causes large pressure transition to the control valve. Again, if the control valve is oversized, the control valve will be operating at low load condition most of the time, which means that the valve is taking most of the pressure differential. Therefore, the control valve must be able to handle this pressure differential adequately, especially when it is located near the pumping header. This is another example of a non-functioning control valve. In this case, the control valve is 100% open all the time. Now, the net result is that the return chill water temperature fluctuates wildly. Because of this, the relative humidity in the solid brown in the background swings wildly too. As you can see, the chill water supply temperature is very constant, but the return chill water temperature is inconsistent. Another items that we should consider is the plate and frame heat exchanger. The only difference from the cooling coil is that it uses water and water as a medium of heat transfer. Both the primary and secondary side of the heat exchanger must be controlled to ensure proper heat transfer between the plates. It is essential that the control valves be selected to match the building actual thermal load as closely as possible. Oversizing reduces valve life and causes the valve to hunt. Control valves should be selected with high rangeability, low leakage, and proportional plus integrating control for close adjustment, accuracy, and response time. Let's look at the characteristic performance curves of a heat exchanger. In this particular case, they compare between variable flow primary and constant flow secondary, and variable flow for both primary and secondary. The purple line is the primary flow rate, and the blue dotted line is the delta T. Okay, these lines are the primary flow rates, yeah, and also the primary side delta T. X-axis is the building or the secondary load. Okay, in this experiment, the design primary supply temperature is 3.9 and delta T is 8.3 Celsius delta T. Secondary supply temperature is 5.6 Celsius and 14.4 Celsius return. On the left is when the customer side of the heat exchanger is constant flow and the district cooling side is variable. At a building load of 50%, the required primary flow rate would be 75%, and the resulting delta T is 5.6% compared to the 8.3 Celsius at design delta T. Now, if you take the same building load with variable flow in the customer side and also in the primary side, the required primary flow rate is only 45%, and the resulting delta T is 9.3 Celsius, which is even higher than the 8.3 C design. So, primary control valve are one of the most important single element in the interface with the district cooling system, and proper valve adjustment and calibration will save you energy. High quality industrial grade control valves should be selected for more precise control, longer service life, and minimum maintenance. Variable flow on both sides of the heat exchanger is required in order to maintain a high system delta T at all load conditions. Okay, this is an example of a district cooling plant operation in Malaysia. These data are what the plant is saying. The data here shows the plant output, supply and returning chill water temperature. This district cooling plant is saying an aggregate chill water temperature from all the various buildings within the complex. This plant was designed for a delta T of 7 degrees C. Obviously, the plant output varies between day and night. Although the chill water supply temperature is very constant, the chill water return the chill water return temperature varies between 10 to 12 degrees C, resulting in delta T between 4 to 5.5 degrees C only. The effect of this low delta T is that the plant actually require extra 13% capacity for every 1 degree Celsius delta T differential to meet the cooling load, meaning that the cooling plant has to run extra equipment in order to serve the same load. Okay, this is an example at the energy transfer station performance of that district cooling system. As you can see in purple, the delta T is very erratic, varying between 4 to 7 degrees C compared to 7 degrees C design. Meaning that what it means here is that the combined air handlers control could not give a constant delta T going out from this particular building. Okay, now let us look how a control valve can be used to ensure proper operation of your cooling coil. The energy valve has the capability for 3 control strategies. There are delta T management, flow control, and also position control. You may choose which of these functions that suit your application. For today, I am going to talk about delta T management only. In this particular project, this is a 4-story office building project in Bangi near Kuala Lumpur. 6 air handler units were installed with energy valves. So I'm going to show you the one function that is the delta T limiting that we use for this project. Okay, this particular air handler is located at level 4. The pump for the chill water pump is located at roof level, which is closest to the air handler. Data from Ballymore Energy Valve was retrieved and analyzed using Ballymore Energy Tool software. This is the flow rate over 1 week from Monday to Friday. As you can see, the flow rates vary between 100% early in the morning due to the pull down effect and about 70% in the afternoon. So if you can see also that in the air handler is actually operating less than the peak float for most of the time. This is a blow up of the chill water supply and return temperature and also the delta T. Now the green line shows the delta T timing limiting function setting, which we set to about 10 degrees Fahrenheit. The cyan line shows the actual delta T. As you can see, the actual delta T is being controlled by the valve according to the setting. Okay, this is the power analysis of the valve performance. Again, you can see that despite the cooling coil power and flow rates varying between 50 to 100%, the delta T remains constant. Okay, this is another case of this AHU is located at level 2. Yeah, this is further away from the plant. Okay, again, it's the same thing. The actual load of the air handler is between 70 to 100%. 100% early in the morning, starts to come down in the afternoon. You can also see a dip during lunchtime. Again, you can see that the delta T is found to be constant despite varying flow rates. Bear in mind that this AHU is located further away from the plant. Plotting on the power curve, again, we can see that the delta T at various capacity and flows is maintained at 10 degrees Fahrenheit. Now, why do we consider conserving energy? Obviously, we want to reduce the overall world energy use, although some of the companies or countries wouldn't like it. To protect our environment, to conform to laws and regulations. In many countries, there are legislation for energy efficiency. Therefore, we have to comply to the law. And also, some companies want to improve their corporate image, being green company. And of course, at a personal level, we as engineers, we want to improve energy efficiency in our work. Yeah. So we need something to ensure that we can achieve all this, and control valve, being able to control, can assist in energy efficiency in a building. Okay, this is a energy efficiency project where SEDA, the Malaysian Sustainable Energy Development Authority, provided a grant for energy audit. This is a 20-year-old, 20-story office tower with centralized chiller plant. One of the conditions of the grant is that the building owner is required to institute some energy saving measures to achieve a minimum 15% energy saving between 3 years from the date of audit, or else the building owner must return the grant money if the target is not met. For this project, the building owner also wanted to charge the tenants for the electricity and air conditioning use. This is the BMS screen showing the WAF parameter, flow rate, supply and return temperatures, percentage WAF opening, and cooling energy. From here, we know exactly how much chill water passing through the cooling coil. It enables us to charge the use of cooling energy. We connected the valve directly to the BMS system using a simple connection electronically. These are some photos of the installation. Photo on the left showing Ballymore representative downloading some data directly from the EV for us to cross-check against the data read by the BMS. These are the energy saving measures that we instituted. We installed electrical and chill water submetering. We upgraded the building management software. We installed energy valve for all the AHUs and chill water pumping optimization. Chill water submetering is made easy using the flow measuring function from the energy valve. The flow rate, chill water supply and return temperature data are read directly by the automation system, and we can automatically create a bill to each tenant. So we calculated the energy valve contribution to the overall energy saving, and we found out that 6% can be attributed to the energy valve. Overall, this particular project return of investment takes about 3.5 years. This is a breakdown of energy consumption of the building after the refurbishment exercise. As you can see, 42% of the electricity is consumed by the chiller plant, 30% by the air handlers, and the remainder by small power and lighting. Overall, we managed to save 18% within a year. So the client was very happy. They don't have to wait 3 years to get the 15% savings. Okay, this is a report that we submitted to SEDA back in 2019. Before upgrade, the electricity consumption was 3.1 million kilowatt hour per year. After upgrade, the total consumption came down to 2.5 million kilowatt hour per year, and also the maximum demand of this building came down. I quote from Lord Kelvin: if you cannot measure it, you cannot improve it. So as engineers, we must be able to measure and quantify the parameters in the system that we design to or operate. The energy valve provides you with the necessary tools for you to do so. Yeah, Mr. Alvin Chan from Ballymore, Malaysia will elaborate further next week on the function of the energy valve, I believe. So, in summary, air conditioning and mechanical ventilation system serves multiple functions for our comfort and survival. It is important to have proper control of cooling coil and heat exchanger to produce conditions within acceptable parameter limits. Air conditioning and mechanical ventilation can also be used for disease infection control. For disease control, room humidity is the most important factor that affects virus reproduction and activation. There is an urgent need to provide accurate control of humidity and temperature in the wake of current health pandemic. Proper selection of control valve is very important to ensure that your cooling coil perform as intended. Modern intelligent control valve that combines three functions: balancing, control, and measuring functions, not only ensure optimum coil performance, it also provides ease for data analytics and energy efficiency. We have reached the end of my presentation. I believe the moderator has got some questions from the audience. I will try to answer as many as possible within the time available. If we don't have enough time, then I will answer them in writing. I can be contacted via email at the email addresses shown or my mobile number 601232268884. You can also visit our website www.aharconsultant.com.my or our Facebook page. And with that, I thank you for listening to this presentation. I will now pass back to the moderator.
Thanks, Engineer Arul Hisham, for your fruitful presentation. Thank you so much. And yeah, before Arul answer your questions, so here comes a Primo QR code that I'll show you in a second. And that please scan the QR code now and get connected with us. You'll get latest update through Primo linking page for our next webinars. Okay, Mr. Arul, there are several questions that come see from the question panel. So maybe I read it out one by one so that please have your answer. And as mentioned, if there are time is limited, so in case we cannot answer all of your questions, so we will get back to you through email. Here comes to the first question. How do you control humidity for an AHU with hot water reheat coil?
Okay, thank you, Alan. The cooling coil set point is controlled by room humidistat. Yeah, the cooling coil. In this case, you have an AHU whereby you have a cooling coil and also a hot water reheat coil. So the cooling coil set point is controlled by the room humidistat. When the room humidity rises above the control set point, the cooling coil valve or the cooling coil control valve should open to allow more chill water into the coil. This will ensure sufficient chill water flow into the cooling coil for dehumidification to take place. The effect of the off-coil temperature of the air off-coil temperature will drop and more dehumidification will take place. Yeah, and the hot water reheat coil, on the other hand, is controlled by the room thermostat. Yeah, when the room temperature drops below the set point due to overcooling of the cooling coil, the reheat coil control valve should ensure the sufficient hot water flowing into the reheat coil for sensible heating to raise up the temperature to the comfort condition. Okay, Alan. So I think that's the answer that I can give.
Thanks, Mr. Arul. Yeah, here is the second question. At the furthest point of the system, shall we install a three-way valve on the energy valve even when we use EV?
Oh, okay. It's a very interesting question. Okay, I think the situation depends whether the pumping system serving the air handler is viable or not. If you use variable secondary pumping at part load when all the control valve close, the pump is supposed to reduce the speed. However, there is a minimum speed that the pump need to operate. Normally, I would say about 40% of the maximum flow. So if still there is a small load in the system, which is less than 40%, the pump must still run at this minimum flow, which is at 40%. So you have a pump that running at 40%, but your load could be probably 30%. Yeah. So how do you do that? Now I'm talking about the secondary pump. So this secondary pump, yeah, running at 40%, the load is only 30%. So since the coil flow rate is lower than the minimum pump flow, the excess chill water needs to return back to the plant, isn't it? Therefore, I believe we should have a three-way diverting valve at the furthest point to ensure that the chill water return to the plant. Okay, I hope that answered that question.
Okay, I believe the question is fully answered. And then let's see. Yeah, this is a third question. For system with primary secondary pumping system operating using delta pressure control of the system. For air handler using energy valve with the delta T limiting function, will be able to ensure sufficient flow in the cooling coils?
Wow. Now the question is getting tougher and tougher, Alan?
Yeah, I think so.
Okay. All right. Well, okay, the function of the differential pressure control is actually to regulate the secondary chill water pump speed. Yeah. Okay, the function, and then we look at the function of energy valve. Now, energy valve is to maintain the delta T with a delta T limiting function. You want to maintain the delta T across the coil. Okay. I believe this energy valve has a pre-programmed limiter on the lowest delta T you can set. And it will control the flow rate across the coil to achieve this. Now, if the actual delta T is below the delta T set point, say, for example, you set delta T at 10 degree Fahrenheit, and the actual delta T is at 8 degree Fahrenheit, there is a control logic built in the flow valve, in the energy valve, that will reduce the valve flow to bring back the delta T to the set point. Okay. Now, when the pump operates between, say, 40 to 100%, the system pressure will also change. Yeah, obviously, regardless of what pressure differential across the valve, this valve will regulate itself to ensure appropriate flow rate passing through the valve. Okay, the valve flow output is pressure independent. This is very important. We heard of PI, pressure independent control valve. Okay, so the valve flow output is pressure independent as low as 1 psi differential operating pressure. Okay, so designer can actually size valve and pumps to operate at 3 to 4 psi differential that reduce the pump head and allow for a smaller pump selection. I believe Alvin will actually elaborate more on the function of energy valve on the 28th next week. Yeah, isn't it? Okay, that's my answer, Alan.
Yeah, thank you for a very comprehensive answer. Yeah, got it clear, much more clear. So, okay, let me see again. There's lots of question. Okay, here comes another one. If the EV is on delta T limiting, but the supply air RH is above the required value, will still be able to open the EV even more?
Oh, so if the EV is on the delta T limiting, but the supply air RH is above the required value, can we open up the EV to allow more water in so that you get the RH? Interesting. Okay. The EV or energy valve will maintain the delta T of the chill water in and out of the coil. Now, if the EV is open 100%, but you could not reach the relative humidity, then there could be two possibilities. One is that this coil is could be undersized, therefore you cannot produce any more capacity. Or another possibility is that you have too much of outdoor air coming into the air side. Therefore, the 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 cooling coil cannot dehumidify them. Okay. Now, most people think that pumping in more chill water into coil will improve the output of the coil or produce more cooling. Well, this is not true actually. In fact, cooling coil has its saturation point, meaning after this point, no matter how much water that pump into the coil will not be able to provide cooling. Okay, so I think you need more pumping power to push water through the coil. So so you will find that it will not work. Okay, so I think Alan, that's my answer for this question. Yeah.
Thank you, Mr. Ru. Oh, is there still some question? But unfortunately, I believe that the time is we ran out. So as mentioned, yeah, Mr. Ru, I believe you get back to our audience through email, right? With
Yeah.
their questions.
Sure. Sure.
Okay, yeah. Thank you so much. Once again, thank you for your presentation with very fruitful information for us today. So before we end, please also remember, don't forget to contact our colleagues, Pang, our sales manager in Malaysia, in order to have any questions or assistance that you need help from us. Last but not least, we appreciate your feedback. Please give us a minute from the time to fill out a short survey for us. Just after webinar session, a pop-up window within your browser will appear. Thank you very much. Once again, thank you for your participation. See you next time. Bye-bye.
All right. Still good timing.